concerning a review of some standard tools for classical flow control problems. And then in the second part of the lecture, I think I didn't turn the mic. Sorry. And then in the second part of the lecture, what I'm going to do is review some new results concerning the use of PDE constraint optimization to ask questions about sharpness of certain estimates in mathematical research. Okay, and I think that the timing is actually very good here, and I'm very glad that Professor Raymond was speaking before me, because what he presented is a very nice and natural lead into what I will be presenting now. So Professor Ramond, one of the main points that Professor Ramond made was that when solving feedback control and estimation problems, there is an issue of large dimension, which poses some problems as regards computational calculation of the feedback matrices. And something needs to be done. Okay, so one possibility is to use model reduction techniques. And what I would like to present here is actually a slightly different approach to this idea, where we will actually be using a different, simpler flow model. And this is what I actually began to discuss yesterday. So here's again the setup. So wake flow. We'll be interested in the output feedback control. So we have to take some measurements, velocity measurements here. Our actuation will be the rotation of the cylinder. And the goal is to stabilize the symmetric yet unstable fixed point. Okay, and we agreed to pursue a simplified models based on the Euler equations. So in the practitioners' circles, there is a belief that implicit Euler equations represent a good approximation to Navier-Stokes dynamics, in particular for large Reynolds numbers, where implicit effects are deemed to play a lesser role. What we also argued is that the steady state to the Euler flows are solutions of this nonlinear elliptic boundary value problem, where we have some freedom in choosing the right-hand side function f. And then by choosing the right-hand side function in this way, we obtain flows which are called the Prandtl-Bachelor flows, which feature constant vorticity vortex patches embedded in otherwise potential flows. Okay, and computation of those solutions, in fact, leads to free boundary problems, because the boundary of the vortex is a priori unknown and needs to be found as the part of the solution to the problem. And those solutions represent continuous families, parameterized, for instance, by the area of the vortex. And if we shrink the area of the vortex to 0, while keeping its circulation fixed, we obtain the Feppel point vortex system. So point vortex system discovered by Feppel, which is given by some remarkably simple algebraic relations. So you can think about this as a steady state equilibrium solution of the to the Euler equations in the geometry corresponding to flow as an obstacle with a flow at infinity. This is of course a weak solution, because it features locally unbounded vorticity. Vorticity is infinite. It's like a delta function. Okay. So this is something that belongs to a very fruitful area of mathematical fluid mechanics known as vortex dynamics. There's a lot of research concerning properties of various type vortex solutions in fluid mechanics. Okay. So this is what we are going to use as our model. Okay. So let's forget about Navier-Stokes for the moment and focus on the Feppel system as our model. Okay. So what I'm going to do is apply precisely the tools that Professor Raymond described to this very simple model. And as you will see, we'll be able to solve the control and estimation problem explicitly. Okay. Even some calculations can be done analytically. And then it will also make it possible to make some forays into the nonlinear regime. We'll be able to prove some theorems about the behavior of the fully nonlinear system, this nonlinear Febel system. Okay, so let's start with some stability analysis. So we have an equilibrium, and the first natural question to ask is whether or not it's stable. Okay, so we perform a very classical stability analysis, and what we see is that well, the system being four-dimensional, we have four eigenvalues, one purely real, corresponding to a growing mode, purely real and positive, another real and negative corresponding to a decaying mode, and there is a conjugate pair of purely imaginary eigenvalues, which correspond to an sort of oscillatory mode. And as you will see in the subsequent analysis, this oscillatory mode will actually play a very important role. Okay? So actually there is some deep connection between the Febel system as I described it and what is happening in reality. So if you look at the orientation of the unstable subspaces associated with the eigenvalues, then you will see that the way the symmetry of this equilibrium is broken during the onset of instability mimics what is actually happening in during the Hopf bifurcation in actual fluid flow. Okay, so at least at the initial stages, the way the instability develops is quite reminiscent of what is happening in a real Navier-Stokes flow, which is, I guess, one of the reasons why this model is well, so useful. And let me emphasize that this model has only 4 degrees of freedom, and for that little cost, it seems to capture a very significant amount of physics. So before we can apply the control theoretic tools, the tools of the linear control theory, we need to ensure that the internal structure of this model is such that actually makes it possible. Okay, so we have to check the controllability and observability of this model. Now let me remind you that the control action is represented by the rotation of the obstacle, which is modeled by a point vortex embedded inside the obstacle, whereas our measurements, the system output, is in the form of velocity at the flow center line. Okay, so we can study controllability just by investigating this standard rank test for the state and control matrix. And what we see is that the rank of the matrix is 2, which is 2 less than the dimension of the system, which means that it's actually not controllable. Okay? On the other hand, when we ask similar questions concerning observability and consider the relevant test, then we see that the system is actually fully observable. Okay? So it's not controllable, but it's observable. Now, what really matters here is not so much controllability, but stabilizability. And to see what is happening, we can convert the system using this very simple orthogonal transformation to the so-called minimal representation, which is both controllable and observable. So in doing this, allows us to separate the modes which are controllable from those which are not controllable. And when we do this, we immediately see that the 2 modes which are controllable are the ones associated with real eigenvalues, the decaying and growing eigenvalues, and the ones which are not controllable are associated with the imaginary eigenvalues, associated describing the oscillatory modes. Okay. By the way, there are also other ways of actuating the system. So another very classical technique represents distributed blowing and suction on the walls. That's in practical applications. This is a very popular way of actuating the flow, where you distribute blowing and suction in the vertical direction on the wall. And one can ask similar questions as regards controllability for our problem if we use this type of actuation. This can be modeled by placing pairs of sinks and sources, which can be done very easily in the context of the potential theory. And then when we do this, then we actually see that with this form, subject to this form of actuation, the system is actually completely controllable. And That's actually, I think, an interesting insight. In the fluid mechanics community, there seems to be, among practitioners, there seems to be a consensus that, at least for this type of flows, blowing and suction tends to be more effective than rotating the cylinder. And this analysis might perhaps offer a hint why this is happening. Okay? So even at the level of the potential flow description, blowing and suction gives rise to a controllable system, whereas cylinder rotation does not. Okay, so how do we find, well, first of all, how do we set up the problem? So we're looking for a stabilizing feedback control, represented by the matrix K, where X prime is the state of the system, which will minimize some performance criterion. Okay, we do allow for noise both in the system and in the measurements, which gives rise to the to the canonical form. And we set up a problem which is known as the linear quadratic Gaussian compensator, which is exactly the type of approach that Professor Raymond described, combining state estimation and linear feedback. Okay, so the idea is that first one uses the available measurements to run a state estimator, which produces an evolving state estimate of the system, and then our feedback operator is applied to this evolving state estimate. Okay, and those two things taken together are oftentimes referred to in the control literature as the compensator. So this is exactly the type of approach that Professor Raymond described, and since his presentation was far more rigorous, I'll just describe this very, very briefly. So it's known that such a stabilizing feedback control can be found by solving an algebraic Riccati equation, so that the closed loop system is stable, and this cost functional is minimized. Of course, when dealing with problems described by systems of large dimension, solving this Riccati equation is a significant issue. Now, we actually have a problem that has 4 degrees of freedom, or actually even 2, because we are looking just at the controllable subsystem, and the Riccati equation for the system can be actually solved analytically. Okay, so this is an example that lives at the opposite extreme in terms of complexity. Okay, because we have a problem that can be solved basically with a pencil on paper. And likewise, we have a similar result concerning the state estimation. So the optimal estimate, which minimizes the error covariance given by this expression, is given by the solution of the following estimator system, where the feedback matrix L is obtained by solving this algebraic Riccati equation, which again can be done very easily in this problem. And since Professor Raymond's description of this approach was far more thorough, I will probably say no more about this here. So before I go on to discuss the results that can be obtained with this approach, let me spend some time discussing some nonlinear aspects of the problem. So one of the advantages of taking a look at this very simple model is that with its very simple analytic structure, we can actually obtain insights about the underlying nonlinear system. And here's what we can do. So the minimal representation that I introduced at the previous, one of the earlier transparencies, can be regarded as the composition of the state space into 2 subspaces. There is the stable subspace, and the maybe I should say that this is the controllable subspace, and its complement. So the control that can be described, that can be designed using the approach I described, is only acting on this part of the system, which is the controllable part. Okay. What it does is it will stabilize the otherwise unstable origin, and it can only affect, because of the structure of the system, the blue part. Okay? And it is, of course, designed based on the linearization of the system. Okay? Now, we also have the red part, which is the uncontrollable part. And this uncontrollable part is characterized by this matrix A11, which has purely imaginary eigenvalues. Okay? And in order to be able to assure ourselves about the stability of this entire system, we would like to be able to say something about the stability of the system, of the subsystem, which is uncontrollable. And at the same time, we know that if the Jacobian of that system has purely imaginary eigenvalues only, then the linear stability analysis is just inconclusive. And we do have to go to the nonlinear terms to obtain some further insights. Okay, and a proper way of studying those type of questions is provided by the dynamical systems theory in the form of the so-called invariant manifold analysis. Okay, so what one is looking for is a map between this subspace, the controllable subspace, and the uncontrollable subspace that will connect the two, and such that the dynamics will always be contained to this manifold. That's why it is called invariant manifold. The precise definition of invariant manifold is as follows. This is the subset of the state space, such that if our initial condition is in that subspace, if it's in that set, the subsequent evolution will be confined to that manifold. And using tools of dynamical systems, we can actually construct this manifold, which turns out to have an exceptionally simple form. It is just zero. And the proof is just by direct calculation, if we substitute this into our system, okay? And then we can show that this identity, this relation, in fact, defines an inertial manifold in the sense that if we start with on a manifold defined by this property, we're always going to stay there. Okay. So this is very important because it allows us to decouple this subsystem from the second subsystem, and then what we would like to do is, well, finally the answer question about the stability of this uncontrollable system, and this can be done by considering the reduced system, reduced to the center manifold, and then the Lyapunov stability for the system can be proved just by considering the Hamiltonian of the original system reduced to this. So it's a little bit technical, although the main idea is rather straightforward. Okay, so this is more or less what I wanted to say about the theoretical background. By the way, if you're interested in the details of the proof, I can send you copies of the paper in which we published this. So let me now show you some computational results, because they are, I would argue, quite interesting. Okay, so there's a couple of figures here. So the first figure shows, well, our cylinder and the two Feppel vortices. So those red crosses represent the equilibrium configuration. Okay? Now, what we do is perturb the one of the vortices away from the equilibrium, and the system being linearly unstable, we see that the vortices immediately escape to infinity. Okay? So this is what happens when there is no control. And now what we do is, in this figure, we actually plug in the LQG control, so this combined estimator and controller thing that I described at the earlier transparency. And what we see is that, well, the states no longer escape to infinity. Here is, by the way, magnification of the neighborhood of one of the equilibrium points. But instead, the state, which is denoted by the red line, ends on a sort of elliptic trajectory, circumscribing the origin. Okay. So what happens is that now that the control starts to act. By the way, the blue line represents the trajectory of the Kalman filter of the estimator system. So we see that the blue trajectory is actually following the red trajectory quite well, which means that the estimator is actually doing a fairly good job here. So what is happening here is that the controller prevents the state from escaping to infinity, as it was designed to do. However, is unable to bring the state back to the equilibrium. Why? Well, because there are some modes, there is a subspace which is uncontrollable. So once the state lands on the uncontrollable subspace, which is this subspace here, that the controller cannot do anything about it, because it's not controllable, okay? However, the dynamics of this on this center manifold is stable. That's why we have this very stable motion over the along this elliptic orbit. So in other words, this elliptic orbit is basically the center manifold whose presence was stipulated by the theorem that we proved on the previous transparency. Okay, so it's an interesting instance as calculation actually demonstrates certain results that were proved in theory. It's always reassuring. Okay, well, it's interesting to see what happens. Okay, so here everything was done using our Febble system as the model of the instability. And of course, from the point of view of real applications, we don't care about the Febble system, we care about Navier-Stokes. Okay, so what I would like to show you now is the result of what happens if we apply this methodology to control just a two-dimensional Navier-Stokes system. Okay, so the way it will work is that the compensator, this combined estimator and controller, will be receiving some measurements in the form of velocity and the flow center line that will be coming from a Navier-Stokes simulation. However, our compensator will be thinking it is controlling a Febble system. So it will estimate the positions of the Febble vortices that correspond to what those measurements represent, and then the feedback control will be applied accordingly. So let's see what's going to happen. I have an animation to illustrate this point. So what I need to do is just open the file. Again, this work was done about 10 years ago, and animations are generated using some ancient technology, which doesn't work with modern viewers, so that's why I have to do this in this way. Okay, so what happens is this. We start with the unstable flow. This is the unstable fixed point, which, well, goes unstable. So you'll see that the symmetry is broken and vortex shading develops. And those two circles represent the positions of the Febble vertices as estimated by the Kalman filter. Okay, so what happens next? Our controller applies the feedback control based on the position of these two vertices. Okay, and would you see that although close to the obstacle, the vortices are in fact quite intense. When you look far downstream, the flow is in fact remarkably symmetrized, which was basically the goal of this exercise. So in our cost functional, we sought to minimize the transverse velocity component, and well, we see that this is happening. That the flow downstream is actually remarkably symmetric. Two more comments. You see that these two vertices, okay, which are actually the positions of the Febble vortices estimated by the Kalman filter, seems to be dancing around an elliptic trajectory, which is again precisely the center manifold, which we saw in the whose existence was stipulated by the theorem we proved. And the second comment I wanted to make is that well, this model is based on inviscid equations, on Euler's equation, and I guess it's well known in fluid mechanics that inviscid models are not really very accurate close to the boundary where viscosity is important. On the other hand, they are expected to perform well far downstream where nonlinear effects play a major role. And in fact, this is what we observe here. our controller doesn't really do a good job close to the boundary, but far downstream, it does what it is supposed to do. Okay, so let me maybe close that. Oops. Okay. Now, there seems to be some evidence that this concept of center manifold in controlled vortex systems is actually quite generic. Here's a snapshot of an entirely different study, which considered a somewhat different control problem. This was a vortex flow past a vertical plate, which was represented using a cloud of vortices. This was actually an investigation carried out by my Italian colleagues. And they were also interested in applying some control strategies to achieve some objectives. Details are not really important. What I think is remarkable is that when you look at the trajectory of the centroid of this cloud of vortices, which is actually drawn here, you see that it also follows some sort of elliptical trajectory. Okay, so while no theoretical analysis has been carried out in this case, there seems to be a compelling evidence that a center manifold of the type I shown you in the Pebble problem might be hidden there as well. Okay, so I think here I will conclude the first part of my presentation. There's one more thing I would like to add. A couple of years ago, so this area of control of vortices has been actually quite active, and there are many interesting results. I guess the appeal is that vortex dynamics offers a convenient low-dimensional description of otherwise infinite-dimensional problems in fluid mechanics. A couple of years ago, I was asked to write a review paper about control problems in vortex dynamics, and I've brought a couple of copies of this paper, so I'll be very happy to distribute them. If there's not enough, it can be downloaded from my webpage, so I'll put those papers for you here. So unless there are some questions, I'll probably move on to the next part of my presentation. Okay, so now we are going to switch gears quite a bit. While what I have described up to this point is rather classical, in the spirit of what I think should be done at the winter school, and concerned problems that, were considered sort of cutting edge 15 years ago, but now are well understood. And I will present you some applications of control and optimization techniques to address some other emerging questions in fluid mechanics. More specifically, I would like to show you how those methods can be used to ask questions whether certain mathematical estimates are sharp. And those questions will concern problems at the heart of mathematical fluid mechanics, namely concerning the existence of smooth solutions for the Navier-Stokes system in 3D. Okay, I have to acknowledge a number of my collaborators. This is joint work with my student Diego Ayala. Also, Mohamed Farazmand was with us a couple of years ago. My colleagues in the department, Nicholas Kevlahan and Dmitry Polinovsky and Charlie Daring from University of Michigan. So here's the brief outline of my presentation. So first I will review some classical estimates concerning Navier-Stokes system in different dimensions. So I'll be brief. My understanding is that Professor Sritaran intends to cover those questions in more detail during the tutorial on Saturday, right? Yeah. So I'll be rather brief here. And then I will argue that questions concerning whether or not there can be loss of regularity of solutions in finite time can be framed in terms of whether or not those estimates are actually sharp. And this, in turn, lends itself to analysis using variational optimization methods. And this is going to be the main theme of my presentation now. Okay? I will show you some results concerning saturation of estimates in 1D and in 2D. And then, time permitting, I may try to present yet another investigation that falls into that category, where methods of PDE control are employed to sharpen certain classical theories in physical fluid mechanics. Okay, so Navier-Stokes, 2D or 3D. We are mostly interested in the formulation in the periodic domain. So while in the past we were concerned with flows that pretended to have some industrial relevance, okay, now we are just considered a purely academic case of the Navier-Stokes system on a periodic domain. Okay. Now, in the 2D case, the existence theory is quite complete. We know that for initial conditions with which are smooth and of arbitrary size, smooth solutions exist globally in time. Okay, so it's satisfactory. What is not the case, however, in 3D, where existence of weak solutions, which may or may not be smooth, can only be proved globally in time, and this result basically goes back to Larrey in the 30s. Okay, classical solutions were proved only to exist for finite times in 3D. Okay, so that's since existence of smooth solutions globally in time hasn't been established, what it means is that it is possible that solutions may actually lose regularity in finite time. Okay, this is the so-called finite time blowup. Okay, and this question is very important. This concerns whether or not the Navier-Stokes system actually makes sense as a model in natural science. And the importance of this question was recognized by the Clay Mathematical Institute as one of the millennium problems for the mathematics community, bearing a suitable monetary price. Okay. Well, as I guess Professor Sritaran will say on Saturday, there are many different angles of attack from the point of view of mathematical analysis on this problem. One approach relies on studying certain quadratic quantities, such as the entropy, which is defined as the L2 norm of vorticity. So we take the curl of velocity, obtain vorticity, and take the L2 norm of that. Okay. Now, there are several different results which more or less say the following thing: the solution remains smooth as long as the entropy is bounded. Okay, and Poyage and Temam proved some theorems concerning this result, although there are now different versions of this result. So what this means is that, well, if the solution, if you consider a classical solution, then entropy is a nice function of time. Okay, and then we can trace it, and the question we are trying to answer is whether or not the entropy may grow so rapidly that it will become infinite in finite time. That's the key question I would like to answer. And I'm going to show you how methods of control can actually, in principle, help us obtain insights about this question. So what we want to know, or what we would like to do is have some estimates over how entropy can grow. So in other words, we would like to bound dE dt, the rate of change of the entropy. And this can be done using, well, first of all, the momentum equation, Sobolev embeddings, Young and Cauchy-Schwarz inequalities, although somewhat intriguing, the incompressibility condition is not really used in those estimates. Okay? So in 2D, the rate of growth of entropy is upper bounded by some constants, time the entropy to the power 2, and then employing the energy equation together with Grunwald's lemma, we can actually show that entropy is always bounded, which implies solutions for existence of smooth solutions for all times. On the other hand, in 3D, because of how the Sobolev embeddings work, the estimate that we obtain is different and now has a power of 3. And we cannot do much beyond that, and as far as I know, that in terms of bounding dE dt, this is the sharpest estimate available to date. Okay? And if we treat this estimate as a differential equation and integrate it, then we see that it blows up in finite time. Okay? So just based on this estimate alone, one cannot rule out the formation of singularity in finite time. And the question concerning blow-up can be therefore rephrased in terms of whether or not this estimate is sharp. In other words, can we find solutions to the Navier-Stokes system that actually realize this estimate over some finite window? Okay? And this can be done with the help of methods of PDE control. So there are, in fact, two types of questions that have to be addressed. Okay? The first question, which I call the small question, concerns whether or not the instantaneous estimates are sharp. Okay? So we would like to know if those estimates, which are written for a specific fixed instant of time, can be saturated. That's the what I call the small question. But then there is the other question, namely, in order to have blob in finite time, those estimates have to be saturated in a sustained manner over a finite time window. And that's what I call a big question. Can we find fields that sustain those upper bounds over a finite time window? Okay? Which, at least computationally, will lead to very different issues and problems. Okay? Let me perhaps at this point make a disclaimer. So, of course, there's no way this sort of approach can resolve the Clay problem. Because the Clay problem is essentially a problem in mathematics where a rigorous proof is required. However, what one hopes here in this line of research is to provide certain insights or conjectures to mathematical analysts which can guide them in attacking the Clay problem. Okay, so this problem has already had some history, and I guess it goes back to Charlie Daring, who was the first one to ask those questions and actually obtain some answers. So he looked at the instantaneous problem and phrased the question I have just stated in the form of the following variational problem. Okay, so he was looking for the velocity field in H1, okay, with some prescribed entropy that would maximize the instantaneous rate of growth, okay, of entropy. Now, d dt can be expressed in this form using the Navier-Stokes equation, and E0 is the parameter. So they actually solved this problem using a gradient-based descent method, pretty much in the spirit of what I described yesterday. And here's what they obtained. So there is one parameter here, namely E0. So what they did was solve this problem for different values of E0, ranging over several orders of magnitude. Okay, so here is E0. And here we have the maximum rate of growth. Okay, and then when you look at this power law and look at the exponent, you see exactly, well, almost exactly 3. Which means that they computed a velocity field which saturate this estimate. Okay? You can find a family of vector fields which, at the fixed instant of time, saturate that estimate. Okay, here's what they look like. Okay, this is the vorticity field that corresponds to the upper branch. By the way, there are 2 branches, a lower one and upper one. The problem is, since the objective function is cubic, the problem is not convex. Hence, the presence of multiple maximizers is to be expected. And for every value of entropy, maybe not every, but for many values of entropys, they do find 2 maximizers, and that's the one corresponding to the higher branch. Okay? Well, of course, while this is quite interesting, it doesn't, of course, resolve the blow-up problem, because we only know that at one instant of time we can saturate that estimate, but to have blow-up, we would need to be able to saturate that estimate over a finite time window. Okay? So this brings us to the second question. So this is the problem we would like to be able to solve. Okay? We would like to find the initial condition in H1 with prescribed entropy, such that will maximize the rate of growth of maximize the value of entropy achieved over a finite time window. And then, of course, the idea will be to see how this depends on E0 and how it depends on the length of time and so on. Okay. So in principle, I believe that problems of this type are or will be within reach of the computational technology that we have, and hopefully in a couple of years we'll be able to solve this problem. There is one technical issue here, namely when you look at the objective function, it involves a max, which is of course a non-differentiable function. So here we have an instance of a non-smooth optimization problem. In numerical optimization, there is a very active area of research concerning non-smooth optimization, and there are many exciting developments there. That said, those methods are still rather experimental and are not really capable to be used to solve large-scale practical problems like this one. So while this remains our goal for the future, let's try something simpler. So Burger's equation. Okay, let's look at similar questions concerning the familiar Burger's equation given here, subject to periodic boundary conditions. Entropy is defined in this way. Now, of course, for Burger's equations, we have global in-time existence for arbitrary data. So, of course, there is no Clay problem. So why bother? Well, for Burger's equation, and also for the 2D Navier-Stokes equation, we can obtain very similar estimates for the rate of growth of various quantities as the ones obtained for Navier-Stokes. And the question whether or not those estimates are sharp is quite relevant. Okay? Because if you can see that those estimates are sharp and they are obtained using very similar methods as for the 3D Navier-Stokes system, then this would offer some reassurance us about what can happen for 3D Navier-Stokes system. Okay, so the rate of growth of entropy in 1D is bounded by this expression, where we have now an exponent of 5/3, and in finite time we have this expression as an upper bound, which asymptotically for large values of the entropy gives us this. Okay, what this means is that if we consider Burger's dynamics and have initial condition with entropy is 0, then what this estimate is telling us is that no matter how long we wait, the solution may not develop entropy that is larger than the initial entropy to the power 3. That's a sharp estimate. Okay? And what we are going to do now is see whether it is sharp, in the sense that we can find actually such solutions that build up that much entropy. Okay? So before we should yes.
Getting such estimates.
Oh, you mean this one or this one? It's pretty much similar as in 3D Navier-Stokes system. So you basically multiply this equation by the Laplacian of uxx, integrate by parts, and then estimate terms one by one.
You don't use the Pola transformation. You don't use the Pola transformation.
Kolhopf, no. Although my colleague Dmitry Polinovsky, whom I mentioned as my collaborator on the second slide, actually redid this analysis and obtained the same essential estimates using Kolhopf. But the thing is that, well, I guess in this case they are using the same methods as for Navier-Stokes because Kolhopf is not available for other systems. So, okay. But the idea is that, well, you basically obtain an equation for d dt and then bound terms one by one using Cauchy-Schwarz, Sobolev embeddings, and yeah, just standard results, a standard exercise in functional analysis. Perhaps Professor Citran will say more about this on Saturday. Okay. Okay. So there are two estimates. There is the instantaneous estimate and the finite time. Let's look at the sharpness of these estimates. Okay. Now for the instantaneous estimate, this is the what I call the small problem. This was studied by Charlie Daring and his student Lulu, which considered the following variational problem. Okay. So they're looking for the field U in H1. It will maximize this subject to this constraint. Quite straightforward. And d dt is given by this expression, so that's what they wanted to maximize. Ether is a parameter, and what is remarkable about their solution is that they found the solution in closed terms. They found an analytical expression for the solution, which is, however, quite complicated, involving elliptic integrals and Jacobi elliptic functions, but it's a closed form solution. Okay? And again, if you plot the entropy here on the horizontal axis and the maximum rate of growth of entropy on the vertical axis, and then look at the solution, then the power law that you see is exactly 5/3, which means that the solution they found actually saturates the instantaneous estimate given here. Okay. However, well, we are ultimately interested in the finite horizon problems. So when you take this instantaneous maximizer, so the solution that saturates the single time estimate, and use this as the initial data for the Cauchy problem for Berger's equation, okay, and then do this for different entrophies, here is how much growth of entropy you actually see. Okay, so if you start with this entropy, that's how much you get. Okay, and the exponent is actually 1, which is a long shot from the exponent of 3, predicted by the analytical bound. Okay, so there is quite a bit of a gap between the mathematical upper bound and the growth of entropy obtained from the instantaneous maximizers. Okay? So what we are going to do is to use the methods of PDE constraint optimization I described yesterday to see if we can find solutions that can do better than this, perhaps even saturate this estimate. Okay? So here is the statement of the problem. We're looking for the initial data for the Berger's equation, which is subject to this condition that will maximize the entropy at the end of the time window. So there are two parameters. Okay, one is E0, is you can think about this as the radius of the unit ball in the space H1, okay, where you start, and capital T is the length of time that you wait. Okay, so you can think about this problem as find a solution on the unit ball in H1, on a ball in H1 with the radius E0, such that in finite time it will get furthest away from the origin. Okay. Well, optimality conditions again were the computed pretty much in the same way as I described yesterday for Berger's equation, except that now we have to take care of the constraint, which is done using the classical method of Lagrange multipliers. So nabla is the Lagrange multiplier. So the way it works, maybe I'll make a very brief digression on the blackboard here. So if you want to take care of the constraint, I construct a new, the so-called augmented cost functional, which is a sum of the original cost functional, augmented by the following term, where we have Lagrange multiplier times the constraint. So E of phi minus E0. Okay, and so this constraint is scalar. So it means that the Lagrange multiplier is also scalar. So we see that if the constraint is satisfied, of course, this term turns into 0. Well, how do we find such maximizing solutions? Again, familiar gradient flow, discrete gradient flow I discussed yesterday, where the gradient, nabla j, is obtained from the adjoint system. So this is an example of the problem where, again, the adjoint has to be integrated backwards in time to give us the sensitivity information. And now, it's absolutely crucial then that our maximizer lives in the sublet space H1. So it's very important to make sure that this gradient actually lives in this space, which is done using the technique I described yesterday. Okay? And then the second issue is enforcing the constraint. So it turns out to be actually very simple. So let's say that this is the constraint manifold, okay? And this is where we are. Our gradient tells us to go there. And what we do is we always make sure to move along this manifold simply by projecting on the manifold, okay? Which is just a matter of dividing by the norm of the expression. That is actually quite straightforward, okay? So that's the method. It's very straightforward, off-the-shelf technique of the type I described yesterday. Let me show you some results. So there are two parameters, the length of the window and the value of entropy. And here is what the optimal initial conditions. Okay, so we're looking for the initial condition that will give us the largest growth of entropy in finite time. And here is what the initial conditions look like, depending for fixed entropy, depending on the length of the window. If the window is very short, then we get something that looks like a shock wave. Why? Well, because if you want to get very largest growth of entropy over a very short window, we don't have enough time for the solution to build up things, okay? So it already should have a shock in it. Now, on the other hand, if the window is long, then the solution has a lot of time to rearrange itself, and somehow it finds it optimal to start with a rarefaction wave, okay? That's what the solutions look like when we plot them for fixed time and different E0. So now I'm going to show you the two most important plots. So here is what the entropy looks like as a function of the length of the time window. So this is the length of the time window. This is the value of the entropy. Every point here represents the solution of an optimization problem, which itself may require thousands of iterations. So there's a lot of computational time that has gone into generating this picture. Okay, so every dot corresponds to a solution of a problem with this length of the time window and this value of the entropy. Now, when you plot this using the entropy E0 as the independent variable, then look at the envelope of the different curves, it shows a very nice power law. So looking at the envelope is mathematically equivalent to computing the max function. Okay, and we see a very clear power law. And the exponent is actually 1.5, which is certainly more than 1 that was exhibited by the instantaneous maximizers, but still way below 3, as predicted by the analytical theory, okay? Which may indicate that, that estimate is in fact not sharp and may still be improved, okay? Well, one can derive a whole bunch of power laws from this data. For example, one can ask the question how the time when the maximum was attained scales with E0, and we obtain a very clear exponent of -1/2. Now, all this approach is based on local first-order optimality conditions, okay? And based on this characterization alone, there is no way we could figure out whether or not the estimates we are computing, the solutions we are finding, are local or global maximizers. There's just no way we can know whether or not our maximizers are global, other than perhaps performing an honest search in the optimization space. That, of course, will not replace a rigorous proof, but I don't think that's within reach in this problem. So, what's the best way to search in infinite dimensional space? Well, look at directions which are orthogonal. Okay, try to probe in orthogonal directions. So that's actually quite straightforward in H1. So in the space H1 on a periodic domain, orthogonal directions are just given by trigonometric functions with different wave numbers. Okay. So the results I showed you. So what we did was compute the maximizers using initial guesses characterized by different wave numbers. And here's what we obtained for wave number equal to 1, and here's what we obtained for wave number equal to 2. They look sort of, they do share some features, but they're not exactly the same. Okay. However, there exists a change of variables, both independent and dependent variables, in Burger's equation, which leaves the equation invariant. Okay. And if you apply precisely this change of variables to those solutions, which look rather different in the original variables, but in those rescaled variables, they actually collapse. And changing the wave number of the initial guess is can be interpreted as rescaling the domain, just taking a subdivision of the domain, if you like, okay? So what happens is that even though we found what appears to be a countable infinity of local maximizers, they all seem to be nothing but rescaled copies of one master maximizer. So they are just one and the same solution in disguise. So here is a cartoon which illustrates that. So if we start with one initial guess, we get this solution. If we start with an orthogonal initial guess, we get another solution. But this other solution is just a rescaled copy of this guy. So what happens if we take an initial guess that, like this one here, is a linear combination of these two orthogonal functions? Well, depending on parameters, you either end up here or here. We, meaning Diego, my student, did a very honest search looking for other solutions, and everything we found was always a rescaled copy of this master maximizer. While this is far short of being a rigorous proof, but it does offer a degree of reassurance that perhaps we found all maximizers. Well, there is a slightly different perspective on this problem that I would like to describe briefly, which is also sort of gaining some traction in the computational blow-up community. So at every fixed instant of time, solution of Berger's equation can be regarded as an analytic function of the space variable. Okay? As such, it can be considered to be a restriction to the real line of a complex-valued meromorphic function defined on the complex domain. Okay? Now, how can one characterize the smoothness of such functions? Well, classical results from harmonic analysis is that the smoothness of such functions can be characterized by the width of the so-called analyticity strip, which is the distance from the real line to the nearest singularity, characterizing the complex extension of the function. Okay? So another way of looking at the blow-up problem is to consider complexified versions of the equation, which has singularities in the complex plane, and then see whether or not those singularities can actually collapse onto the real line. If they do, this means blow-up. If they don't, solutions remain smooth. Okay? And in fact, there is an increasing number of computational studies where people are studying complexified Navier-Stokes or complexified Euler equation, and, which have singularities outside the real line, and then are trying to see what happens with those singularities. There are many technical issues with this because there are questions: which independent variables should one complexify? Maybe time. Okay. So here's an analysis of our results from this perspective. So here are 3 sample trajectories characterized by the entropy and the associated width of the analyticity strip. So we see that at the instances of time when the entropy of the solution is maximal, the width of the analyticity strip is becoming the smallest, which means that the singularity characterizing the solution of the Berger's equation is getting the closest to the real axis. Although, of course, since we know that this system is regular globally in time, those singularities can never collapse on the real line. Okay? Well, this is a potentially interesting way of rephrasing the optimization problem as one defined on the complex plane. Why? Well, because instead of working with the PDE, one works with a bunch of singularities. This is basically a discrete problem. Okay? So this is, I think, a potentially promising research direction for the future. Now, let me tell you something about similar problems for 2D Navier-Stokes equation. Okay? So in 2D, as is traditional, at least in certain circles, we will be working with the vorticity equation. Okay? Omega is vorticity. Psi is the stream function. They are connected by this Poisson equation. Now, a compact way to write the 2D vorticity equation is indicated here, where J is just this expression for the Jacobian determinant. Okay, so it's a sort of compact way of writing vorticity equation in 2D. Now, entropy. Well, entropy in 2D is for flows on flows on periodic and unbounded domain is uninteresting. Well, because due to the absence of the so-called vortex stretching in this term, entropy can only decrease. So it's uninteresting. Entropy cannot grow. Okay, so it's trivial. Now, things become more interesting if you look at the evolution of the gradient of vorticity. So you obtain the equation just by applying gradient to this expression here. And we see here that in this equation already we have a stretching term, which is a nonlinear source term, pretty much similar to the vorticity stretching term in the 3D Navier-Stokes equation, which is believed to be at the root of the problem with regularity. Okay? And the associated quantity with this equation is called the polynstrophy. So here we had entropy, now we have polynstrophy, which is basically the L2 norm of the vorticity gradient. Okay? And for convenience, we are going to express everything in terms of the stream function psi. So again, the question we are asking is how much polynstrophy can grow in 2D flows. Okay? And of course, it's a purely academic question because we know that 2D flows are globally regular. However, we do have estimates for the rate of growth of the polynstrophy, and would like to know if those estimates are sharp, because they are obtained using very similar methods as the estimates for Navier-Stokes. And if they are sharp, what the fields that maximize those estimates, that saturate those estimates, look like. Okay? So
This is essentially the H2 norm you are tracking.
Exactly, yeah. So while in the past we were looking at the H1 norm, H1 norm is uninteresting for 2D Navier-Stokes, so we are tracking H2 norm. Exactly, yes, thank you. So it's the H2 norm of velocity. Yeah. Okay, so the expression for the rate of growth of polynstrophy is just obtained by straightforward manipulation and has this form. Okay, and there are two estimates available for the instantaneous rate of growth. One obtained by Charlie Dering and the other by Diego. Those estimates are different than the corresponding estimates in 1D and in 3D for the following reason. You will see that on the right-hand side, we actually have two quantities. In addition to polynstrophy, we have either entropy in the first estimate or K, the kinetic energy, in the second estimate. Okay? Whereas in 1D and in 3D, find the instantaneous estimates have only one quantity on the right-hand side. Okay? This will have far-reaching ramifications for how we set up the variational problem. Okay? Well, you can say that entropy and energy and polynstrophy are all linked via Poincare inequality. That's certainly true. And we can use Poincare inequality to eliminate energy and entropy to get an estimate which is in terms of only one quantity on the right-hand side. However, we know what functions saturating Poincare inequality look like. They are just eigenvalues of the Laplacian. So we know that going from here to here may in fact implying the loss of smoothness. Okay, so since we're interested in the sharpness of estimate, that sharpness may be lost here. So that's why we prefer to work with those estimates involving two variables, even though it's computationally much more challenging. Well, and there is a bound on the maximum growth of polynstrophy in finite time, which features second power of the initial polynstrophy. Okay. So, so the question is, are the instantaneous estimates sharp? So this question can be reformulated in terms of this variational problem, where we are looking for the stream function psi in H4 that will maximize the rate of growth of polynstrophy. We need H4 because of this term. Okay, to be able for the rate of growth of polynstrophy to be well defined, H must be in H4. Okay, subject to two constraints on entropy and polynstrophy. Well, how do we solve this problem? Well, again, discretized gradient flow. So that's the continuous gradient flow. And that's the discrete version. Now, how do we compute the gradient? Well, we compute the gradient using the sort of variational techniques I described yesterday. It's a straightforward, albeit a little bit tedious exercise. And we do this, and again, it's absolutely critical that the gradient we use here lives in the right space, which is H4 here. Actually, in the computations, when we were working on this problem, due to some error, at some stage we used a wrong space, and this was complete garbage. Okay? So this looks like a nitty-gritty technical detail, but in fact, this is absolutely central to construct solutions in the right space here. Okay? Well, we are talking about estimates, so after all, that's not that surprising. So the way we proceed is first we derive formally an L2 gradient, and then using the Sobolev gradient technique I described yesterday, we obtain the H4 gradient via a solution of this elliptic boundary value problem, where we actually have the Laplacian to the power of 4. Okay, it's because we look for a solution in H4. Okay, so that's why we have such a high order of this differential operator here. Now, the structure of the L2 gradient is actually quite interesting. So when you use methods of calculus of variations to differentiate this expression, the L2 gradient looks like this, which features a sum of 3 terms, which exhibit some interesting, almost cyclic structure. Okay, they all have Jacobian determinant. They all have bi-Laplacian and Laplacian, which are sort of distributed in 3 different ways. Okay. Okay. By the way, this is the Euler-Lagrange equation for our variational problem, and I'm wondering about the techniques to actually solve such equation. I know too little about this, but I wouldn't be surprised if problems of this type would be amenable to treatment using Lie group methods or something similar. So, if any of you have some ideas, I would be delighted to have some feedback. Now, there is some technical issue that I'm not really going to discuss in more detail here. So, while in the past we are looking for a solution that was to be subject to one constraint, and we took care of that just by projection. That was fairly straightforward. Now we are actually looking for now we have a problem with 2 constraints, which means that we are looking for solutions that have to live at the intersection of 2 nonlinear constraint manifolds in an infinite dimensional space. And computationally, this is much harder to solve because well, the projections simply don't work. Well, one could say that one could use the method of Lagrange multipliers. That's certainly true. However, methods based on Lagrange multipliers involve linearization, and if one does this iteratively, repeatedly in an iterative process, it does give rise to a buildup of an error in the satisfaction of the constraint. This is a benchmark problem, so we do want to satisfy the constraint with the machine precision. Okay, so the precision 10 to minus 6 is not enough. We need 10 to minus 12, okay, because of the subtlety of the problem. But this can be done, so it's kind of complicated and probably outside the scope of this lecture. Well, so here are some results. So we are interested in this estimate, okay? So we treat entropy as a parameter and p as a variable. So here is p, and entropy is fixed at 100 or 1000. Hence, we get 2 curves. Now, as I said, entropy and polynstropy are not unrelated. They have to satisfy Poincare inequality. So polynstropy can only be larger than some value given by the Poincare limit, which is given by the red line in every case. Now, the black lines represent the linear part of this constraint. And we see that, well, I guess the curves computed numerically. So every point on those curves represents the solution of a variational problem. They actually capture quite well the linear growth. Here is a slightly different perspective on this problem. Now, when we look at this estimate, it actually has two parts. There's the linear part and the quadratic part with negative sign, which actually limits the growth. And what I think is quite interesting is that the computed maximizing growth of polynstrophy actually captures this effect. Okay? That there is a maximum value that can be attained, which is also present in the estimate. I think it's quite interesting. And here is what the maximizing fields look like. Okay, so if we are very close to the Poincare limit, then we know that the maximizing field must be very close to the solutions which turn Poincare inequality into an equality. And those are, of course, eigenvalues of the Laplacian, which on a 2D periodic domain are just the adic products of trigonometric functions. And that's what we see here. This is basically sine x, sine y, okay? Which is the maximizing solution near the Poincare limit. Now, as we allow polynstrophy to grow, we see that something, well, interesting is developing. And then we see this vortex structure developing, which then shrinks in a shape-preserving manner as we allow polynstrophy to increase. Okay? So, well, let me maybe summarize this part. So, well, instead of a summary, I just put up a table that puts together all the available estimates regarding the instantaneous and finite time problems in 1D, 2D, and 3D, together with information, as we know it now, concerning the sharpness of those estimates. Okay? So, in this work, we focused on the cases in blue. So, finite time Burger's equation, which we found not to be sharp, and therefore perhaps open to improvements. Working with a number of analysts, and some of them tried to do this, and so far there's no success. Nobody has been able to sharpen this estimate. For the 2D Navier-Stokes system, well, there seems to be evidence that this instantaneous estimate is in fact sharp. The next thing to do that we are already working on is the finite time estimates for the 2D Navier-Stokes system. And of course, out there looming on the horizon is the big 3D Navier-Stokes system. And as I said, well, I guess, at least in principle, the computational tools are in place. Just this computational size of the problem is formidable. But maybe in a couple of years, we'll be in a position to have a shot at that as well.
So which of these are periodic boundary conditions?
Yes, this is all subject to periodic boundary conditions. Yes. Yeah, that's how the sort of regularity problem is typically stated. Yeah. Okay, so I guess I have another 10 minutes or so. So in this time, I would like to present yet another application of variational optimization methods to refine or sharpen a problem in sort of physical fluid mechanics. It has to do with the so-called Krishnan-Lead-Batchelor theory of 2D turbulence. So while up to this point, I've been focusing on the initial value problem for an autonomous system, so no forcing. Okay. Now, from now on, I would like to consider the Navier-Stokes system subject to body forcing. Okay. So in fluid mechanics, there is a large group of people studying turbulence problems, and this is the typical model, a mathematical abstraction of real turbulence, where all the forcing by exogenous noise, whatever, is lumped into right-hand side forcing. Okay? We'll consider problems which are homogeneous, isotropic, and statistically stationary. Okay? So in 2D turbulence, which is the study of chaotic behavior exhibited by two-dimensional flows, one of the sort of key theoretical results is the so-called Krishnan-Lead-Batchelor theory. Okay, so this is something that has nothing to do formally with Navier-Stokes. This is just a scaling argument in principle, which predicts how the spectrum of the velocity field should scale with the wave number. Okay, so for those type of problems, people typically work with the energy spectrum, which is basically the spectral density, plotted as a function of the wave number. That's the key quantity of interest in this very large community. And the key result that is due to these three scholars predicts the following. If we imagine that the forcing here on the right-hand side is localized in this band of wave numbers, okay, then this theory predicts that the energy will cascade to lower wave numbers, meaning larger scales, and will exhibit a power law with the exponent minus 5/3, while entropy will cascade to higher wave numbers, meaning smaller scales, exhibiting an exponent of minus 3. Okay? So that's a sort of physical theory based on some, which is not really rigorous, but is based on some scaling arguments. However, it's very well established. Okay? It's a sort of cornerstone of phenomenological fluid mechanics. Okay? So the question we are asking is, maybe before I specify the question, let me state one more fact. There are a couple of rigorous results due to Konstantin and Ted Shepard, which basically say the following thing. If there is no large-scale dissipation, okay, for a system with forcing, then the exponent in the polystrophy range must be greater than minus 5. So if there is no dissipation here, this slope must be very steep here. If we do allow for large-scale dissipation, okay, then mathematical analysis allows for this exponent to be in the range between minus 3 and minus 5. I'd like you to bear in mind this result as we move on. Okay. So what is the question that we are asking on? That we are going to ask? Well as the KLB theory is embedded in sort of turbulence research, it tends not to be well verified. Okay? So if you ask the question, can you actually find flows that satisfy this theory? The answer is unfortunately no. If you do a numerical simulation of 2D turbulence, then while you do see minus 5/3 in the energy spectrum, in the entropy spectrum, you typically see much steeper slope, minus 5. Okay? So that's this is what has kept people puzzled for a number of years. Okay, so the question we are asking is, can we actually find a forcing for which the KLB theory work? Okay, and this can be framed as a variational control problem. Okay, which is stated in the following manner. Okay, so we have a cost functional, which basically represents the misfit of the actual spectrum and some prescribed spectrum. Okay, so we say that we want the flow to exhibit certain spectrum, which is the spectrum stipulated by the KLB theory, okay, with exponent minus 3 here. And we are looking for the forcing that will give rise to this spectrum, which mathematically is framed as this variational problem. Okay? So in this case, our forcing is a function which is L2 in space and in time, which means that we are looking for a function that depends on both space and time. In principle, one could consider functions which are just stationary in time. There are many different ways in which this can be framed. Okay? And that's, again, that problem lends itself to a numerical solution using the adjoint-based techniques I described, although details tend to be more complicated, but in principle, the idea is just the same. So I'll skip those details and just show you some results. So here's the optimal forcing. Here is what the optimal forcing looks like as a function of the wave number for different times. But what is interesting is actually shown here. So while conventional meaning just random forcing gives rise to this rather steep slope, the optimal forcing will give a slope of minus 3, which is precisely what we asked for. Okay? And, well, this is the vorticity field corresponding to the conventional forcing, and that's the vorticity field corresponding to the optimal forcing. Okay? And we see that it actually exhibits a rather different structure featuring really small-scale features. There's an interesting aspect of this solution that I would like to describe. Here is what the energy injection looks like as a function of the wave number. Okay. So the first thing that we are looking for was not band limited. It was allowed to live in the entire spectrum. So what the variational formulation found for us is something that is peaked at some intermediate range of wave numbers, but has a negative sink for very small wave numbers. Okay? So let's now scroll back to Konstantin's theorem, which said the following. If we want to have a slope between -3 and -5, and we are asking for -3, then necessarily there must be a large-scale dissipation. So this is what we observed here. Okay? Since we asked for a slope that is rather shallow, -3, by Konstantin's theorem, we know that there must be a low wave number dissipation, which the forcing, which the variational formulation found for us. So that's again interesting that the results computed numerically are consistent with some rather abstract mathematical theorems about Navier-Stokes. So actually, the reality, I mean, as interesting as it might appear, the reality is not that rosy, because this problem actually turns out to be rather ill-posed, in the sense that the solution, the spectral properties of the solution do not have a continuous dependence on forcing. So if we take our optimal forcing and perturb it just a little bit, okay, then the whole thing falls apart. Okay, so this solution is not very robust. Okay, if we take our forcing and just add some very small level of noise, the whole thing falls apart, and we don't see the -3 slope anymore, or anything even close to it. Okay. So what does this tell us? Well, it tells us that mathematically the KLB theory might be correct, might be consistent, because there do exist forcings that give us that slope. However, they might be physically irrelevant, because in the function space, they represent a very sparse set. They might be just isolated points. Physically, that doesn't really, not very interesting. Okay, so I guess I'm close to having exhausted my time. I'll just mention a few references. I couldn't resist the temptation to put up first Charlie Daring's paper, which was foundational as regards looking at questions concerning sharpness of estimates in terms of variational optimization problems. This is this paper here, and a couple of our contributions to this work, some of which are still under preparation. So here are the papers concerning the earlier part of my presentation. I'll stop here. I'll thank you for your attention, and we'll be delighted to answer questions. Thank you. Viscous effects. Oh, that's in this problem. Oh, this is in regard to the first problem. Well, it's an interesting question. So the Feppel system is a weak solution of Euler equation. So as such, there is no viscosity. Okay. However, sort of implicitly, the effect of viscosity might be modified by the fact that if we apply forcing via rotation of the cylinder, then the system no longer satisfies Kelvin principle, which means that the total sum of vorticity in the flow domain is not constant. So this might be thought of as a model for viscous effects. Other than this, we didn't do anything. Okay. Other questions, comments? If not, I'm going to be here until Tuesday evening next week. So I've already had a number of interesting discussions with some of you, and look forward to continuation. Well, thank you again.